Welcome to The Explainer. Today, we are going on a journey, a deep dive into the world of numbers to uncover the hidden patterns and the secret logic that governs pretty much everything, from simple puzzles all the way to the security of our entire digital world. Okay, let's get into it. So, let me just ask you something. It might sound a little strange, but have you ever wondered if numbers have secret identities? You know, if they have these hidden properties that you just can't see by looking at them? Well, it turns out a lot of them do. Okay, let's start with something you can actually see. This is called a strobogrammatic number. Basically, it's a number with a kind of physical symmetry. When you flip it completely upside down, it looks exactly the same. Digits like 0, 1, and 8 are just naturals at this. But this is where it gets really cool. The magic happens when other digits get in on the action. Take a number like 69. It works because when you rotate it, the 6 becomes a 9 and the 9 becomes a 6. They're a perfect pair. And that lets you create all sorts of combinations, like 818 or even 906, which flips to become 609. Okay, so that's physical symmetry, right? Something you can see with your own eyes. But what happens if we start looking for symmetry in a totally different language? I'm talking about the fundamental language of all our computers, binary. Well, that's where you find what's called a binary palindrome. We're not looking at the physical shape of the digits anymore. We're looking at their fundamental code of ones and zeros. And if that sequence reads the same forwards and backwards, it has this special kind of digital symmetry. Let's actually see what this looks like. Take the number 16. In binary, that's 1, 0, 0, 0, 0. If you reverse it, you get 0, 0, 0, 0, 1. Totally different. But look at the very next number, 17. In binary, it's 1, 0, 0, 0, 1. Flip it around, and it's exactly the same. That is a perfect binary palindrome. All right, so we've seen visual patterns, we've seen digital patterns. Now let's switch gears a little bit and look at a classic logic puzzle that's going to uncover something way, way deeper about how numbers are actually put together. Because this puzzle, it's going to show us that some numbers have these truly secret identities. And it's not about how they look, but about their fundamental properties. So here's how the puzzle goes. You've got 100 closed doors and 100 monkeys. Monkey number 1 goes and toggles every single door. Then monkey 2 comes along and toggles every second door. So 2, 4, 6, and so on. Monkey 3 toggles every third door. You get the idea. This goes on for all 100 monkeys. So the big question is, at the very end, which doors are left open?
Okay, so let's break this down. A door's final state, whether it's open or closed, it all comes down to how many times it gets toggled. Take door number 13. It only gets visited by monkey 1 and monkey 13. That's 2 toggles. So open, then closed. It ends up closed. Door 50 gets toggled by 6 monkeys. Open, closed, open, closed, open, closed. Back to closed. But then look at door 16. It's toggled by 5 monkeys. Open, closed, open, closed, open. It stays open.
So you see the pattern here. The key, the whole secret, is that the doors left open are the ones that are toggled an odd number of times. And the numbers that get toggled are just the factors of the door number. So what kind of numbers have an odd number of factors? The perfect squares. It's so cool why this works. For most numbers, like 13, the factors come in nice, neat pairs, 1 and 13. For 50, you've got 1 and 50, 2 and 25, 5 and 10, always pairs. But for a perfect square like 16, you have pairs like 1 and 16, 2 and 8. But then there's the number 4, which pairs with itself. That one lone factor, the square root, is what breaks the symmetry and gives perfect squares an odd number of total factors. So you see, that puzzle wasn't just for fun. It actually revealed something absolutely fundamental about the very code of numbers, the importance of their factors. And this focus on factors, well, it leads us straight to the absolute bedrock of number theory, the atoms that all other numbers are built from, prime numbers. These are the numbers that have exactly 2 factors, and only 2, 1 and themselves. So, how do you even find these things? Well, one of the oldest and honestly most beautiful methods is the Sieve of Eratosthenes. Just imagine it's like a systematic hunt, where you just eliminate all the numbers that can't be prime to see what's left. Okay, here's the game plan. First, you list out all your numbers. You start with 2, the very first prime, and you cross out all of its multiples, 4, 6, 8, all the way down the line. Then you just move to the next number that isn't crossed out, which is 3, and you cross out all of its multiples. You just keep repeating this process, and whatever is left standing at the end, those are your primes. Now, this simple sieve is amazing, but when you're talking about finding primes in these massive, massive ranges, mathematicians have an even more powerful tool called the segmented sieve. It basically breaks the problem down into smaller, more manageable chunks. All right, so we've got our primes, we know how to hunt for them. Now we can move beyond just finding them and actually start using their unique properties to solve some really fascinating and much harder problems. And a really powerful tool for that is something called Euler's phi function. It sounds complicated, but here's the gist. For any number you pick, let's say n, it's a super fast way to count how many smaller numbers are relatively prime to it. And that just means they don't share any common factors, other than 1, of course. Let's take 24, for example. Its prime ingredients are 2 and 3. Euler's function gives us a shortcut to calculate that there are exactly 8 numbers smaller than 24, like 1, 5, 7, or 11, that don't share those prime factors. And this ability to quickly count unrelated numbers, it's the secret sauce for a lot of modern encryption. And this power, a power born from primes and factors, it all leads us to one final incredible theorem. It's something that started in ancient China, but it's now absolutely critical to our digital lives. This is where it all comes together. We're about to see how factors, primes, and now remainders all connect in one of the most brilliant tools in all of math. Check out this kind of puzzle. Find me a number that when you divide it by 3 leaves a remainder of 2, but when you divide it by 5 leaves a remainder of 3, and so on. This is exactly what the Chinese remainder theorem, or CRT, was made for. Finding that number feels like looking for a needle in a haystack, right? But the CRT gives you a roadmap. It proves a unique answer exists and tells you how to find it. And for this puzzle, the smallest number that works is 23. But okay, who cares about an ancient riddle? Well, we do. Because this exact same logic is a cornerstone of modern cryptography. The RSA algorithm, which helps keep our online communication secure, relies on principles that are directly related to the CRT. It helps our computers do massive calculations securely and, just as importantly, efficiently. So let's just take a step back and look at the whole journey we've been on, from these simple puzzles to this world-changing power. Think about it. We started with simple visual tricks, like numbers that look the same upside down. Then, a logic puzzle about monkeys and doors showed us the deep importance of factors and perfect squares. That led us to the primes, the building blocks, and finally to the powerful theorems that use those primes to solve ancient riddles and secure our modern world. So here's the real takeaway. The path from a simple little pattern to a technology that changes the world, it's often way shorter and more direct than we think. And it really makes you wonder, doesn't it? What other simple patterns are hiding all around us, in plain sight, just waiting for someone to see them as the key to solving tomorrow's biggest problems?